We have already discussed about the photochemistry of alkene. We know that the alkene undergoes cis trans isomerization. The photochemistry of alkene it undergoes cis trans isomerization. So if we have a trans alkene, we know that this is thermodynamically more stable, but under photolytic condition, there is a pi star excitation, and then there is a loss of double bond, and the free rotation is possible, and then we end up with the cis alkene. So this is it is possible to convert photochemically most stable trans isomer to cis isomer, but it is not possible to convert 100% because it's always in equilibrium, and it is an example of non-adiabatic photochemical reaction. This is second type, cis trans isomerization followed by cyclization. Cis trans So if the substituent at cis position are properly, the nicely set, as then it may also undergo under photochemical 6 pi electron sciences. So if we have a system of say trans stylbene H nu goes to cis stylbene trans to cis stylbene. So if we can write both the phenyl groups in this manner, and then this further undergo under photochemical condition undergo the 6 pi electron cyclization. 6 pi electron cyclization. So it gives a dihydrophenanthrene. Goes here. This is now change. Goes here. So dihydrophenanthrene, and this is this gets aromatized very fast under air oxidation. So, but the photoproduct is dihydrophenanthrene. So this is an example of, so we have a cis trans isomerization, followed by cyclization if the substituents are properly set under cis orientation, may undergo further. We also looked at third type of photochemical reaction. If we have COC6H5, if we have a trans 1,2-dibenzoyl alkene, 1,2-dibenzoyl alkene. So as usual, under photolytic condition undergo cis trans isomerization to give cis 1,2-dibenzoyl alkene. This is cis 1,2 dibenzoyl alkene. Now this when the two benzoyl groups are in the cis orientation, it undergoes further we can further photochemical reaction to undergoing phenyl group migration. So this arrangement called dibenzoyl alkene rearrangement. So if you can write this molecule in this fashion, C6H5 . So the under photolytic condition, excited carbonyl adds to this, and then we end up with a 6-member transition state. There is an oxygen here. Right, you have double bond. You have C6H5 H, and then this can write a positive charge. The dipolar species, as deuteronic species, is well known in enone system. So we can write like this, and then this goes like this. There is a cleavage of this bond. So this bond cleaves. So this is the cleavage of this bond. So when this bond cleaves, there is a phenyl group migration to the other benzoyl group. So we have an H here. So we end up with a system like this. We have OC6H5. The phenyl group of this goes to other side. This, of course, there is a CH5 here. There is a double bond. There is a ketene. Is a ketene intermediate. And this ketene gives in the presence of methanol, gives an ester, and if there is a presence of some moisture, going to give an acid. So so far we have learned this. These are this photochemistry of photochemical reaction of open changes. Now what happens in the photochemistry of cyclic alkene? Photochemistry of cyclic. So here is an example of pH, and then is another example is a pH. So this cis is still bean, and this is 1,2-diphenyl cyclobutene, 1,2-diphenyl cyclobutene. This is a highly very strong fluorescence, gives very highly fluorescent, highly fluorescent, and this is very weak fluorescent, gives a weak fluorescence. And then and it has been found that methanol quenches the fluorescence of the 1,2-diphenyl cyclobutene. Methanol quenches 1,2-diphenyl cyclobutene to give a to give ionic product. So the highly fluorescent, the methanol, the irradiation of this irradiation in methanol irradiation in methanol quenching of fluorescence takes place. Quenching of fluorescence takes place to give ionic product. So when the irradiation of 1,2-diphenyl cyclobutene is carried out, H nu in the presence of it goes to an excited X1 state. It under under hydrocarbon RH, the presence of hydrocarbon, the loss of fluorescence takes place, and then the hydrocarbon loss of fluorescence takes place, but which is a these are this is nothing but they are ionic dipolar species is well established, and then this dipolar species, I mean the excited state of the 1,2-diphenyl cyclobutene, 1,2-diphenyl cyclobutene in the presence of methanol ROH leads to, so there is an abstraction of a methanol ROH. Abstraction of a proton by this anionic species become H, as PH is a phenyl group, here the positive charge, and now this positive charge in the presence of methanol undergoes the addition products OCH3 pH. So the photochemistry of cyclic alkene such as 1,2-diphenyl 1,2-diphenyl cyclobutene, which is highly fluorescent, and there is and it has been found that this highly fluorescent compound, the quenching of fluorescence takes place when irradiation in methanol, irradiation of this in hydrocarbon. Quenching of fluorescence takes place to give the anionic product. So quenching of irradiation, the in hydrocarbon, quenching of fluorescence takes place in hydrocarbon. So let's modify this. Quenching of fluorescence takes place in hydrocarbon, and the gives ionic products, gives ionic product in protic solvent. So as so you can see that the 1,2-diphenyl cyclobutene, 1,2-diphenyl cyclobutene under photolytic condition goes to an excited singulated state, and then in the presence of hydrocarbon, quenching takes place by losing fluorescence, and under protic solvent the dipolar species in the excited state is gives the methanol added product. So Interestingly, non-Bourne, another example of cyclic alkene. Cyclic alkene like non-Bourne. nor non-Bourne. So this has been found to give different product depending upon the medium used. So under photolytic condition, if we have a in the when R is equal to phenyl group, then this goes via S1 state, and then of course the ionic species R is equal to methyl group H nu. R is equal to alkyl group, R is equal to methyl group. Then the reaction goes by a triplet state, and then it goes a diradical species. So here is an ionic species. So pH is a positive charge, here is abstraction of, and then here it goes a abstraction of is a radical product, is a ionic product, leads to ionic product when R is equal to, in the case of non-Bourne, when R is equal to phenyl group, reaction goes via excited singlet state, and then if if R is equal to alkyl group such as methyl, the reaction goes via triplet state. This is the radical derived product. So it has a pH, and then you have a radical product. So these are now coming looking into the more examples of cyclic unboarding methanol. The irradiation of non-Bourne in methanol. Methanol with xylene. If xylene is a sensitizer, so let's see if you have if we have a H nu plus methanol with xylene as sensitizer. Irradiation non-Bourne methanol in methanol with xylene as sensitizer gives interesting products, and you can see that it is methanol, irradiation non-Bourne in methanol under photolytic condition in the presence of xylene as the sensitizer. It gives non-Bourne radical plus CH2OH radical, and then this via the reaction takes place via T1 state, and now this gives different products. We can see the radical coupling, CH2OH, plus there is a possibility of the abstraction of a hydrogen atom to give an aldehyde plus, and also self coupling of this. So, and then plus the aldehyde plus non-borane plus CH2O. CH2O aldehyde. So this is a disproportion. This is the addition product. This is coupling. Coupling product, and this is disproportionation product. So you can see the non-borane in the presence of methanol xylene as the sensitizer under photolytic condition. It generates a non-borane radical plus CH2 radical from methanol group abstraction of an hydrogen atom by the excited excited state of the double bond, and then this radical undergo different. Can see the product. One is a disproportionation product, coupling product, and third one is the addition product. And another cyclohexene, photochemistry of cyclohexene. Has also been reported, and if we have this one in the presence of methanol ROH, and then the sensitizer is acetophenone COCH3, it gives the ionic product via, it gives OR plus pH ionic product via S1 state. So and this 2-phenyl cyclohexene in photic solvent, photochemistry of 2-phenyl cyclohexene, 2-phenyl in photic solvent. Now if we have a larger ring system such as cyclooctene, a 2-phenyl cyclooctene, under photolytic condition. It has been found that in presence of under similar condition such as in methanol and acetophenone as the aceto pH COCH3, acetophenone as the sensitizer, as in the case of cyclohexene here. Here it has been found that it doesn't give the addition OR and pH. So it doesn't give no addition product, no addition product. But on the other hand, the cyclooctene is, the ring size is large enough, is a 8-membered ring, it's large enough to undergo distortion, and this undergoes cis trans isomerization across double bond because you can twist to orient in the trans. So we can, so it has been found that it gives a phenyl group here, is a 5-member ring, and then you have 1 2 3 1 2, and then you have So let's write in a better way. It gives right. There's a phenyl group here. This is an H here. 1, 2, 3, and then this. So you can see the and then it says so large enough to undergo cis trans isomerization photolytic condition. So it takes place in this particular case. Okay, so this for today, and thank you very much.